In this next lesson, we're going to talk about exponential functions. We have talked about exponents before. We know all the rules of exponents. We know how to deal with them. But now we're going to take a look at them from the point of view of functions. And so what is an exponential function? An exponential function is just going to be a function of this form. F of x equals b to the x, where b is not a variable, b is a constant. B is a number that you know. So for example, f of x equals 5 to the x. That's an example of an exponential function. The b is called the base. So in this concrete example, the base is 5, and the variable is the exponent. We generally do not want the b to be negative, at least not in college algebra. If the b were negative, then we would be uh, going into the realm of complex or imaginary numbers, and we're not going there. And also, we don't want to allow equals 0 or b equals 1 because those are the trivial cases. Those are the non-interesting cases. Basically, nothing happens in those cases. Because 0 to the anything is just going to be 0, or 1 to the anything is just going to be 1. So we normally then say b, the base is neither 0 nor 1, and it has to be positive. Okay, so that is the exponential function with base b. So here's a concrete example with the base b equals to 2. So in order to figure out what the graph of this function looks like, we can start by making a table of values and plug in a bunch of different random numbers, easy numbers, whole numbers, so you can easily plot them. So suppose you plug in 0. So 2 to the 0 is 1. And then suppose you plug in 1. 2 to the 1 would be 2. So I'm plugging in the numbers in here. So the function we're considering is f of x equals 2 to the x. So when you plug in 0 here, 2 to the 0 is 1. When you plug in 1, 2 to the 1 is 2. When you plug in 3, 2 to the 3 is 8. When you plug in 5, 2 to the 5 is 32. When you plug in 10, 2 to the 10 is 1024. And then you can also plug in negative numbers. 2 to the negative 1. So when you plug in negative 1, 2 to the negative 1, that's a negative exponent, so that's the same as you flip. So this is 1 half, or 0.5. 2 to the negative 3. So again, that's a negative exponent you flip. And then the exponent will be positive 3. And then that means 1 half by itself 3 times. Or you can distribute the exponent. This is 1 cubed over 2 cubed. 1 cubed is 1 and 2 cubed is 8. So that's 1/8. Or in decimal form, that would be 0.125 and so on. So you plug in numbers, positive and negative, and you get that. And then with those numbers, you can plot them all on the Cartesian plane, and you can get the graph of y equals 2 to the x, or f of x equals 2 to the x. In the graph, here it is, right here. The graph of y equals 2 to the x is right this one. Y equals 2 to the x, this one right here. And similarly, you could do the same thing for the base being equals 1 half. You plug in a bunch of numbers to get the values, and you plot them, and you would see that the graph of f of x equals 1 half all that to the x is going to look like that. So here's some of the basic properties of exponential functions, of this function of this form. The domain is everything. That means you can plug in any number and you're never going to get an error in the calculator. It makes sense to plug in any number. You're never going to get error. Okay, so this is defined for all real numbers. So you can plug in anything. The range, meaning remember the range is the vertical span. The range is from 0 to infinity because an exponential function like this never dips below the x-axis. So all the values are above the x-axis, meaning 0 and not including 0, but from 0 and above, not including 0. You can never plug in a number in there and get 0. So 0 is not going to be in the range. That's not a possible output. Any other possible number, any other positive number is a possible output, is an actual output of something. And then these graphs are going to have asymptotes. An asymptote is a line, in this case I'm talking about a horizontal asymptote, is a line to which a graph gets arbitrarily close. So this graph, if you move to the left, it gets arbitrarily close to the x-axis, to the line y equals 0. It gets arbitrarily close. So if you keep moving all the way to the left, the graph keeps getting closer and closer and closer and closer to the x-axis. It doesn't really ever touch it, but it gets closer and closer and closer indefinitely. Okay, that's an asymptote. That's what an asymptote is. In this case, we're saying that the x-axis is a horizontal asymptote. You could have asymptotes that are vertical asymptotes. Um, so, for example, let's say uh, this is a vertical asymptote. Then that means the graph of whatever your function is gets closer and closer to this graph. So it could be like this, let's say. To this line. Like this. It gets closer and closer and closer, but doesn't really ever touch it. So it keeps going like that forever. So that would be a vertical asymptote. And of course, it doesn't have to get close to the line from the left. It could get close from the right. So something like this could also be, let's say now the asymptote is here. Um, okay, so this one right here, you see as you move to the left, you get closer and closer to this vertical line. So that could be also an asymptote, a vertical asymptote from the right in this case. So this is from the left, this is from the right. You could also have an asymptote from below, a horizontal asymptote from below. So what I'm saying is all the exponential functions have a horizontal asymptote like that. The basic ones have the x-axis as the horizontal asymptote. But of course, if you take this function and you transform them by moving everything like by, I don't know, 7 units up, then the horizontal asymptote is not going to be the x-axis anymore. In that case, it will be the horizontal line y equals 7 because you move everything up. So it depends, at least for the basic functions that look like that without any transformation, without being moved to the left or to the right, up or down, or any of those transformations. For the basic ones, the x-axis is the horizontal asymptote. So the graph gets arbitrarily close to the x-axis. Now, these two graphs right here, it turns out that they are pretty typical of what all exponential functions look like. This one right here is representative of what all the exponential functions look like if the base is between, if the base is bigger than 1. So if the base is bigger than 1, then the graph is going to look like that for sure. So this graph is typical or representative of the graphs of all exponential functions when the base is bigger than 1. And this one right here would be representative of all the exponential functions where the base is between 1 and 0, between 0 and 1. So all the exponential functions that have a base between 0 and 1, the graphs are going to look like that. So for b bigger than 1, the graphs rise as you move from left to right, and for b between 0 and 1, the graphs fall as you move from left to right. Okay, so in other words, For b bigger than 1, these are increasing. And for b less than 1, these are decreasing. Okay, so be careful not to confuse power functions with exponential functions. These two functions are completely different. So don't confuse x squared this is a power function with 2 to the x. This is an exponential function. In the exponential function, the variable is the actual exponent. In a power function, the variable is the base. Okay, and of course they have completely different graphs. This one in this particular example, that's a parabola, and this one we just said looks like that. Okay. Now the basic properties um, of exponential functions, well, these are just the laws of exponents, which we have already discussed at the beginning of the semester. But there's a couple of properties that are new, that are going to be new. First, let's go over the old ones. If you're multiplying two exponential functions and the bases are the same, then you can add the exponents. If the bases are the same, then you can add the exponents. If the bases are not the same, then you cannot do anything, unless the exponents is the same. And in that case, you can just combine them like that. So if you have two bases be multiplied and you have an exponent, you can distribute that exponent like that. This is rules that we knew from before. And dividing two exponents with the same exponential function with the same base, you can just subtract the exponents. You can distribute exponents like that over a quotient. A over b, all that to the x equals a to the x over b to the x. And then if you have two exponents back to back like that, you just multiply them. And if you have a negative exponent, then it's the same as just flipping the thing and keeping the exponent positive. All right, so here are the properties that are new. Well, this one I already mentioned, but if b is bigger than 1, then this, as a function, it is increasing all the time or everywhere. And if b is between 0 and 1, the function is decreasing everywhere. This property that we're mentioning here now is that no matter what you plug in an exponential function, b to the x, regardless of what the base b is, you're always going to get a positive number. And that is you can see that visually from the fact that all the y values of any x that you get, when you plug in any x, the corresponding y value is always above the x-axis. So that means all the values are positive. The entire graph is above the x-axis. So that means all the y values, or the outputs, are positive. You can never get a negative number when you plug in an exponential function. The graphs never dip below the x-axis. In particular, b to the x is never 0. Never ever 0. It's always bigger than 0. So that's another property. Okay. That is helpful when solving equations. And this one right here, that is also even more important and useful when solving equations, is that exponential functions are one-to-one. They're injective. And that's something you can easily see from the graph, because the graphs pass the horizontal line test. Easily pass the horizontal line test with flying colors. Imagine any vertical line right there. For either of these two graphs, they're different graphs, they're going to pass the horizontal line test. So that means they are injective. And what that means is that if you have two different exponential functions with the same base, so you have different different exponents, I should say. If you're evaluating the exponential function at different points, then if the outputs are the same, that means the inputs must be the same. So let's say this is my exponential function. If I have that f of x equals f of y, which is another way of saying that b to the x equals b to the y, because when you plug in x here, you get b to the x. When you plug in y, you get b to the y. If this is true, because we know the function is injective, that means that eventually this has to give me x equals y. So if I have that these two things are equal, I can conclude that x must be equal to y, because this is one-to-one or injective. Two, if the outputs are the same, the inputs must be the same. If the outputs are the same, the inputs are the same. And now we're going to put those properties to work to solve some equations. Let's solve some simple equations. Okay, the first equation right here says, we have to solve for x in all of them. The first equation right here says find x where pi to the 4x minus 1 equals pi to the 4 minus x. Okay, this property that we're going to use here works for all bases regardless of what the base is. In particular, it works when the base is pi. Now, this function is injective and have b to the something equals b to the something else. So if we have b to the something equals b to the something else, that means that those two things, those two exponents, must be the same. They must be equal. So right here, applying that property, pi to the something equals pi to the something else, these two exponents have to be the same because the base is the same. So what that means is then that 4x minus 1 has to be equal to 4 minus x. They have to be equal. And now that is a simple equation that we can solve easily. So put all the x's together on the same side. So move this x minus x to this side, you're going to get 4x plus x. And then move this minus 1 to the other side, you're going to get 4 plus 1. Yeah, I moved to the minus x and then move to the minus 1, the opposite side. This gives me 5x equals 5, and divided by 5, you get x equals 1. And that's the value of x. Okay, that's when the bases are the same. Sometimes the bases are not the same, such as in this one, but you could do a little trick to make the bases be the same. And in this one as well. Let's do b first. Okay, so we see the bases here are not the same, but you can just change it, because if you remember that 9 equals 3 squared, then you can rewrite this as, I'm going to use another color. We can rewrite this as, well, don't do anything to the left-hand side, but we can write the right-hand side as 3 squared. 3 squared. And now they have the same base on both sides. Okay, now using this property, if the bases are the same and you have two exponents exponentials being equal to each other, that means the exponents have to be the same. So that means that 5x minus 7 has to be equal to 2. This is again called using the injectivity property, the fact that exponential functions are one-to-one. If the outputs are the same, the inputs, which in this case are the exponents, have to be the same. Now we solve this. Add 7 to both sides. This is going to be 5x equals 9. And divide by 5. And you're going to get that x equals 9/5. Okay, now let's try this one. Okay, again, this is another one that the bases are not the same, but you can do the same little trick that we did over there. So 25 is actually 5 squared. So you can rewrite the 25 as 5 squared, and then you would see that you will be introducing or rewriting the 25 as something that it has base 5. So you can write the 25 as 5 squared. So that's the 25 to the 3 minus x, which we have to keep there, equals 5 to the x. And now, using the property that when I have two exponents like that back to back, I multiply them, so this is going to be 5, and you multiply that. Multiplying that, it's going to be like this, 2, 3 minus x equals 5 to the x. So you could have done it just at once. This is 6 minus 2x. Okay, this is 6 minus 2x equals 5 to the x. And now we have two exponentials equal to each other where the base is the same for both, namely 5. Now, because the bases are the same, you have them equal to each other, that means the exponents have to be the same. What that means is that then 6 minus 2x has to be the same as x. And now solving for x, you want all the x's on the same side, so let's say we move that over there. You're going to have 6 equals 3x because you add them, plus 2x, you get 3x, and then dividing, you get x equals 2. Sorry, yeah, you divide by 3. So 6 divided by 3 is 2. Yeah, that's correct. So x equals 2. Okay, of course, you could check. One way to check your work is to plug it back in there and see that you get something that is true. We're not going to be doing this, but with all of them. But for example, for this one, if you plug in 2 there, 25, 3 minus 2, is it equal to 5 squared? Oops, I plugged it in there. When I plug in 2, 25 to the 3 minus 2, is it true that that's equal to 5 squared? Well, simplifying, that's 25 to the 1. Is it true that that's equal to 5 squared? Well, yes, because 25 to the 1 is 1, and 5 squared is 25. 25 to the 1 is 25, and 5 squared is 25, so both are the same. So you can check your work by plugging that back in there. You don't have to if you are sure you didn't make any mistakes. Okay, and last one. I think you should pause the video and try that on your own. And now let's do it. Okay, so this one have different bases that we cannot work it out like that. So we're going to, I mean, not yet. Later we're going to learn another method to tackle it without doing this. But for now, we're going to change the bases so that you have the same base. So if you remember that 2 to the 4 is 16. 16 is actually 2 to the 4. 2 times 2 times 2 times 2. 16 is 2 to the 4. We can rewrite this one like this. 2 to the 4, that's 16. And then copy the exponent, 2x minus 3 equals 2, 7x plus 2. And now multiply the exponents because these are back to back. This is going to be 2 to the, okay, 4, 2x minus 3. You could have done it at one shot if you wanted to. So now this is 2, 8x minus 12 equals 2, 7x plus 2. And now that the bases are the same, you can set the exponents equal to each other. You're going to get 8x minus 12 equals 7x plus 2. And then subtract. So move the 7x to this side and move the 12 to the other side. 12. 8x minus 7x is x. And you get x equals 14. And that is the answer for that one. Now we're going to be talking about some applications. One of the most frequent applications of exponential functions occurs in compound interest, when computing the value of an investment in the future. There's two types of interest. There's simple interest and there's compound interest. So exponential functions appear in applications where compound interest is being talked about. So there's a formula for computing compound interest. And this formula you don't have to memorize. You should have it. If I put any questions on any of the exams with this formula, then I'm pretty sure that the problem will either show it or you can just have it. You can just have it written out somewhere. I will tell you where there's going to be problems like that or not. Either way, you should have the formula. You don't have to memorize that formula. But the formula is written right here. And you should know what the letters mean. That's what you should know. How to use the formula. And in order to be able to use the formula, you need to know what the letters stand for, what the letters mean. So the formula is A of t equals P times parentheses 1 plus R over N to the NT, where P is the amount of money that you're investing. We use the letter P because the amount of money in an investment is usually called the principal. So that's the amount, the original amount of money that you're going to invest, however that is. But it could be deposited in a certificate of deposit or any other way. So there's many ways of investing money. Okay, anyway. And then, of course, you get paid some interest, and the interest is usually given as a percentage rate, an annual percentage rate. And that is the so-called APR, the annual percentage rate. And the letter for that in the formula is little r, R for rate. And when you put it in the formula, you always have to enter it as a decimal. So if they say that the rate is 10%, you're not going to put r equals 10. You're going to put r equals 0.10 because you have to convert the percent to a decimal. And you do that by moving the dot. So 10%, if r equals 10%, then in the formula you're going to plug in 0.10. You move the dot twice, right? So like 50% is 0.5 or 0.50. You're not going to say r equals 50. Alright, so you express it as a decimal. And then the n is the number of times per year that the interest is going to be applied or computed or compounded. So there's going to be a keyword that is going to tell you how many times per year. They're never going to tell you n equals blah. They're always going to say it implicitly with a keyword. So like you could say use the word monthly, they could use the word weekly, daily, etc. And then n would be the number of times that time period happens in a year. So if they say monthly, then there's 12 months in a year, so that means n equals 12, and so on. So if whatever the keyword implies, um, whatever the keyword tells you, you can figure out how many times that happens in a year, and that will be the n. And then the A in the formula is the accumulated balance, so A for accumulated balance, sometimes also known as the future value. The accumulated balance is the amount of money that you're going to have after a certain time, T years after you made the initial investment. So the T in the formula, which is the last letter that we haven't said, the T is the time. That time that has elapsed. T in years. Okay, so you plug in all those numbers in there, and then the output is going to be the amount of money you're going to have after T years. Alright, so that sounded more complicated than it is. It's actually pretty simple. So here's the first example. Suppose that you have $1,000 and you invested at an APR of 7%. So you're going to get paid 7%. Remember, APR stands for annual percentage rate. We're going to compute the balance after 10 years if the interest is compounded. So there's two parts, two different questions. First, we're going to compute the balance after 10 years if the interest is computed or compounded quarterly, and then we're going to do it for daily. Okay, again, this is actually pretty simple because we have a formula and this is just like a plug and chug type of problem. So the accumulated balance is going to be, so um, let's plug in all these numbers. So P is the original amount invested of the principal. The P is 1,000. So I'm going to put here 1,000. That's for the P. Then you have a 1 plus, and then the R. The R, they just told me what it is. It's 7%. But remember, we enter it as a decimal. So 0.07 is not 0.7, it is 0.07. 0.7 will be 70%. 0.07, you move the dot twice. And then all that over n. N is, there it is given by this keyword, quarterly. If it is compounded, if the interest is compounded quarterly, how many times is that in a year? So quarterly, so quarter, that should remind you like an actual quarter. How many quarters in a dollar? 4. So that means 4. Quarterly means 4 times in a year. And then the exponent is nt. So that means n times t. So n is, we just said n equals 4. Okay, we just said n equals 4. N is the quarterly, a number of times in a year. And then times, I'm going to put a dot meaning times, not a decimal, times time. How much time? How much time we're going to let that investment grow for 10 years. So times 10. You can put some little parentheses there if you want. Times 10. And then we're going to put all of this in the calculator. And look how I'm putting this in my calculator. Okay, this is going to be 1,000 1,000 times, so I'm going to push the times button, times parentheses 1 plus 0.07 divided by 4, close parentheses. and then I hit the exponent button right there, that y to the x, that's my exponent button. And I have to put 4 times 10. However, the calculator, uh, if I enter 4 and then I press times 10, the calculator is only going to understand that only 4 is the exponent. You have to tell them, no, it's the 4 and the 10, the whole thing, the 4 times 10. So that means when you actually put in the calculator, you have to put some parentheses around here. At least for this calculator that is a cheap one. Some calculators you don't have to do that. If it's one of those calculators where you see the exponent real small on the top, then you don't have to do that. But for this one, I have to. So I'm going to put parentheses 4 times 10 close parentheses. So you see that gives me 40, which is 4 times 10. And then I hit the equal sign, and then I get this number, which is 2001.5, and then this is money, so we really have to round to 2 decimals. So if you round that to 2 decimals, that's actually 0.60. Right, and that's it. So this person is going to have $2,000 after 10 years. If they invest $1,000 at 7%, compounded quarterly. Okay, now let's do the next one. It says do the same thing, same calculation, but for compounded daily. Compounded daily means that n is going to be equals to 365 because it says daily. In this one was n equals 4 because it says quarterly. Okay, so other than that, it's all the same deal. So this is A equals, we're still investing this $1,000, it's the same problem. 1 plus is the same APR, that didn't change, over, now the n is 365, and then the exponent is 365 times 10. The n equals 365. Okay, now let's enter this in the calculator, see what we get. 1,000 times, parentheses, 1 plus 0.07 divided by 365 close parentheses. Now I hit the exponent button, and I have to tell the calculator that all that is coming now is the exponent, so I have to put parentheses. Otherwise, again, it will just take the 365 as the exponent, and the 10 is not going to be an exponent for the calculator. So 365 times 10, close parentheses, and you see that's the actual exponent. We multiply 365 by 10, and now I'm done entering everything. Hit the equal sign, and the answer is 2013 point, and then rounding this to 2 decimals is money, that would be 62. 2013 and 62 cents. So even though you leave it for the same amount of time, for the same length of time, 10 years, and you're getting exactly the same APR because you're compounding it more frequently, namely daily, you're going to get a little bit more money at the end of the 10 years. Not a whole lot more, but a little bit more. Okay, now let's do one more of these. Suppose now that you're investing $2,000 at an APR of 5%, compounded monthly. Compute the balance after 6 months and compute it again after 5 years. Okay, this one I think you can try. You can pause the video and try it. Remember that the time t is always entered in years. So because it says months, you have to think, how do you enter 6 months in terms of years? And do it that way. But once you do it, okay, let's compare notes. Let's do it together. So this is going to be A equals, and I'm plugging in just in the formula, A equals P, the P is 2000, parentheses 1 plus R over N, the R is the rate, so it is 5%, but you enter it as a decimal. So 0.05 over N. N is the number of times in a year. It says is compounded every 6 months. Every 6 months, that happens twice in a year. Oh, sorry, my bad. It says compounded monthly right there. It is compounded monthly. Compounded how many times in a year? Monthly. Well, that means n equals 12. So this means n equals 12. Okay. So n equals 12. Times, to the 12 times the time. The time is 6 months. That is half a year. Okay, now that's correct. Now that's it. Compounded monthly means n equals 12. Okay, so now let's enter this in the calculator and see what we get. This is going to be 2000 times parentheses 1 plus 0.05 divided by 12 parentheses, all that to the parentheses 12 times 1/2. Close parentheses, hit the equal sign, and you get 2050, rounding to 2 decimals, that is 52. Alright, and now let's do it for 5 years. This is going to be P, which is 2000, 1 plus the R, which is still 0.05, over N is still 12, and it's monthly. The only thing that is changing here is the T, the length of time. So this is 12 times 5 years. So T equals 5. T equals 5. Length of time the money is invested. T equals 5 years. Okay. Now let's put this in the calculator. We're going to get 2000 times parentheses 1 plus 0.05 divided by 12, close parentheses, to the, now remember you have to tell, in this cheap calculator, you have to put parentheses for the exponent, 12 times 5, which is going to be 60, and then this is 2,566.72, rounding to 2 decimals. So after 5 years, you're going to have that the money is going to grow to 2,566.72 cents. Okay. Now we need to talk about one very important number, special number, in math that is called e. The number pi is a very important number in math, and it can be defined in terms of area. The number pi is actually just the area enclosed by a circle of radius 1. So if you draw a circle of radius 1, the area of that circle is pi. That's what pi is. So the area of this circle is pi. So you can define pi that way. There's another number, again, that is called e, that could also be defined in terms of area. It is not the most intuitive definition, but you could define it many different ways, and the two ways that are easy to understand for college algebra, one of them is in terms of area. The other ways you can actually define E is using calculus, so that's out of our above our pay grade, so we can just define it in this easy way using area. So using area, how do you describe E? Well, E, if you draw the graph of y equals 1 over x, if you draw the graph of y equals 1 over x, you have this curve right there. And if you start at 1, so this is 1, this is 2, this is 3. If you start at 1 and consider the area under the graph between 1 and whatever number, so the shaded region, let's say starting at 1, if you consider the area under the graph starting at 1 and you keep moving and you keep moving to the right, and you stop when that area is 1, you're gonna, I mean, at some point the area is gonna be 1. If, when you're close to 1, the area is really tiny, but then it keeps growing. So if you keep moving to the right until the exact moment when you get that this shaded region, that pink region is 1, right where you stop, that is E. And this spot right here, where you would stop to get that the area of the shaded region is 1, which is the area between the x-axis and the curve starting from 1 and then moving to the right. The area swept between 1 and E under the graph of y equals 1 over x. Okay, that number right there is E. And E, as you can see, is a number between 2 and 3. It's closer to 3 than it is to 2, and the exact value is about 2.71828. That is the exact value of E. So that's one way of defining E. Doesn't seem to be very, very useful, but that's one way of defining it, of explaining what it is. And it is, again, an important number in math. It appears a lot in many different contexts. And it is so important that we actually say um, that we give it a special name, special letter for it. The letter is E, and is E because it was the mathematician Euler who introduced it. And also, when the base is E for an exponent, we're saying that that is the natural exponential base. It is natural, the natural exponential base. It is natural to do calculations when the base is E and to use it in calculus formulas and such. And so that's one way to define it. There's one more way to define it, and it's as follows. If you consider the exponential function, the compound interest formula, where r equals 1, you put here r equals 1, and you put t equals 1, and p equals 1, so you would have, I mean, if p equals 1, r equals 1, and t equals 1, the whole thing just becomes 1 plus 1 over n. If p equals 1, r equals 1, and t equals 1, then this is what you get. So in that expression, if you start evaluating that expression with different values of n, so say n equals 10, n equals 100, n equals 1,000, n equals 10,000, and you keep plugging in numbers that are bigger and bigger and bigger and bigger, and bigger, okay, of course this is going to get bigger, but it doesn't get bigger indefinitely in the sense that it grows without bound. No, there's actually a cap. You cannot go past a certain number. This, as you plug in letters for values for n that are bigger and bigger and bigger, this does get bigger, but there's an actual limit. There's an actual cap for that, and or a bound, upper bound. And that cap or limit is actually e. That's another way to define e. It is the limit of this expression as n becomes bigger and bigger and bigger. So as n goes to infinity, meaning it is becoming huge, this number becomes bigger and bigger, but it is actually approaching e. It gets bigger, but there's a limit to it, and it is e. So using that fact in a little bit of calculus, you can show that actually then when you have an r, and don't replace the r with 1, when you just leave the r like that, and you do put t equals 1, p equals 1, then this expression right here, which is part of the compound formula, when n becomes arbitrarily big, this thing goes to e to the r. So that again, that's another way of defining e. When the base is e, the function is called the natural exponential function. And what does that mean that n is becoming arbitrarily big in the compound interest formula? Remember, the n is the number of times you do it in a year. So when n equals, when you compound the interest in a year. So when you compound the interest in a year only once a year, that means n equals 1. So that would be annually. When you do it monthly, that would mean n equals 12. When you compound the interest weekly, that means n equals 52. When you do it daily, that means n equals 365. But you could do it even more frequently. Then you could do this every 12 hours. Then that would be double that. And so on. You could do this hourly. Then that would be the number of hours in a year. You could do it every minute. Then that would be the number of minutes in a year. And of course, it would get bigger and bigger and bigger. You could do it every second or every half a second. Compound the interest. And that would just mean that the n is becoming bigger and bigger and bigger. Now, when n becomes infinitely large, that essentially means that you're compounding the interest non-stop, or in other words, continuously. So when n equals infinite, that means, or approaches infinity, that means you're compounding the interest non-stop or continuously. And that gives rise to the so-called continuous compound interest. And that is when the interest is compounded non-stop or continuously. And because of that, uh, and this formula comes from by just taking this and letting n become arbitrarily big. So that means you're letting n become bigger and bigger and bigger. And in the limiting value of this is when that becomes e to the r, as we said right here. That part becomes e to the r in the limit. So then replacing that with e to the r, you get this compound interest formula. Okay, so that's the story for that. Using this formula is actually really easy. So the formula is A equals P E to the RT, where P is as before is the amount of dollars invested, E is 2 point whatever, that number is in your calculator. You don't have to worry about that. It's like E is like pi, it's in your calculator. So E in this calculator is right here. Where is it in this calculator? It is right here. That there. Okay, and then the R is as before, the APR, and then the T is as before years, the time in years. Okay, so some people memorize this formula by reading it out loud. You see this PERT, they call it PERT. So that's the continuous compound interest, the PERT formula. Anyway, so now let's use this formula to figure this out. Suppose that $1,000 are invested at an annual interest rate of 7%. Compute the balance after 10 years if the interest is compounded continuously. If the interest is compounded continuously, that means this formula. That's the key word that you know that you have to use this formula instead of the other one. Alright, so then you just plug and chug. So P is 1,000, is the amount of money invested. You have E. The R is 7, but as a decimal, 7%, but as a decimal, so 0.07. And the time is the number of years, which is 10 years. And now let's put this in the calculator. Okay, in this calculator, unfortunately, when you're going to put exponentials with E, it behaves a little bit funny. And you have to put the exponent first and then hit it with the e to the x button. So that's kind of a little weird. But okay, that's the way it has to be in this calculator. So how do you do that specifically? And that's only for the e button. So this is gonna be 1,000 times, and then I'm gonna put the exponent stuff first, and then hit it with the e. So let's see. Times, and I'm gonna put tell the exponent first. Remember, you have to put the exponents in parentheses in this shift calculator. So times parentheses 0.07 times 10. Then I'm going to close the parentheses, which is 0.7. So if you actually multiply 0.07 by 10, you do get 0.7. And now I'm going to hit it with the E button. So e to the x there. And then I hit the equal sign, meaning that I'm done. And that's your answer. You get 2,013.75. Okay, so once again, if you have a cheap calculator, you have to put the exponent stuff first. Remember to put in between parentheses. So 0.07 times 10, and then hit it with the E button, with the E to the X button. So that's kind of backwards. But for exponentials, at least in the cheap calculator, that's how you enter it. Okay, and here's one last example. One last application. So another frequent application of exponential functions occurs with mathematical modeling. Mathematical modeling is when you come up with a function that you can use to predict or just describe uh, some data. You can if you're not going to get any more data into the future, then you can use the function to just kind of summarize uh, all the values that you have But if you're going to use the function, the modeling to predict something in the future, then you can use the function to uh, predict future values. And this is used a lot in biomathematics. Um, as you know now with the coronavirus, mathematical modeling is used to predict. Of course, some of those models have been flawed, but uh, that depends on how good your data is, the assumptions you're uh, using to get to the formula. Okay, so this example right here is directly from the book. So I didn't come up with this model, which is directly from the book, and it says the following. The amount of imports to the USA has increased exponentially since 1980. And the book gives some sources, they're right there. And it says the exponential function, this one right here, where x in this formula is the number of years after 1980, the number of years after 1980. So for example, 1981 would be x equals 1 because that's 1 year after 1980. 1982 would be x equals 2 because that's 2 years after 1980 and so on. Where x is the number of years after 1980. And this formula right here can be used to estimate the total number of US imports in billions of dollars. So you plug in a number for x here, and that tells you an estimate of the total number of imports that happen in that year. So the question is, using that model, that mathematical model, find the total amount of imports. This is again an estimate, it tells you right there, an estimate. Find the total amount of imports to the US in 1995 and also in 2005. And round your answer to the nearest billion dollars. So you're going to round it to a whole number. Okay, uh, so we just have to figure out what to plug in basically. So in 1995, how many years is that after 1980? This will be 15 years after 1980. So that means x equals 15 because the x is the number of years after 1980. Okay, so there are going to be some examples like this in the homework. You just have to take your moment and try to understand what the x or the variable stands for so you can figure out what to plug in. Alright, so that means x equals 15, so we're just going to plug in 15 then. So if 15 is, and now let's plug it in there. So this says 307.368 times 1.072, and now I hit that with y to the x, and then I say what is my x, which is 15, y to the 15. So we do get, after 15 years, 872.128405. In following instructions, we're going to round it to the nearest whole number. Nearest billion, these are billions. So remember, these are billions. So I will give the answer as 872 billions. About. So that's an estimate of the total number of imports that happened in 1995, according to this model. All right, and now to figure it out for 2005, well, 2005 is 25 years after 1980. So that means x equals 25. Now let's plug in 25 and see what we get. So this is 307.368 times 1.072 to the 25. We got 1,747.947,101, and then rounded to nearest whole number, we're going to say 1,748. Okay, that completes that problem.